So our next speaker is Dr. Henry Stapp. Henry did his doctoral work under the direction of Nobel laureates Emilio, Segrè, and Owen Chamberlain. He created the theoretical framework for the analysis of the scattering of polarized protons, and then analyzed data obtained from the experiments at the Lawrence Radiation Laboratory at the University of California in Berkeley, obtaining the phase shifts first at 360 MeV and later at higher energies. His work was the first large-scale computer analysis in high-energy physics, and subsequently he closely worked with Wolfgang Pauli in Zurich on parity violations and on fundamental problems in quantum theory. He wrote an essay there entitled Mind, Matter, and Quantum Mechanics, which developed to a book of the same title published 35 years later. He's written over 300 technical and mathematical published papers pertinent to basic foundational issues. During the 1960s, he was a principal mathematical and philosophical spearhead of the new approach to quantum theory known as S-matrix theory. He worked in Munich with Heisenberg on the problem of interpretation of quantum theory, and later in Austin with Wheeler on the same subject. His paper, The Copenhagen Interpretation, is widely recognized as a seminal work on this subject. In 1968, he wrote his first paper about the apparent need in quantum theory for faster-than-light transfer of information, and this issue had been raised in a paper about the Einstein-Podolsky-Rosen paradox published in 1964 by John Bell. Stapp has been ever since a principal protagonist in continuing developments pertaining to this fundamental issue. His most recent works focus on the strong influence of quantum processes on the working of the brain, and specifically on the fact that quantum theory brings conscious choices by human agents irremovably into physical theory in a way that directly accounts for the ability of a person's conscious choices to causally affect the activity in his or her physical brain. I'm really intrigued by his background, let me tell you. This should be really interesting. And his talk is titled The Action of Mind on Brain, which I suspect will contain a lot more than those simple few words. So our next speaker. Harry.
Actually, the title that I thought I had given, and somehow it got mixed up, was to be Mind, Brain, and Free Will in the Quantum Universe. And that's the talk that I had prepared to give. But after listening to yesterday's talk, I realized I would be asked a lot of questions about how to explain those phenomena in terms of the theory that I had been telling you about, and realized that in order to answer those questions, I would have to deal with some aspects of quantum theory that I was not going to talk about. So I reorganized my talk, and the new title was going to be Understanding the Mind-Brain Relationship and all you heard yesterday. But then I heard Nichols' talk this morning and realized that really that was where I should start, because it really talks about, in some sense, the connection between processes that are occurring in the brain and consciousness. That's at least what he's trying to address. And so this is the third talk here, and version of my talk. And so, as regards Nichols' talk, he called it a reductionist approach, which actually meant that he was really focusing on what was going on in the brain. And every time he mentioned consciousness, he kind of added whatever that is. And so the problem here is the reductionist approach is essentially talking about, or it's closely related to the classical mechanics understanding of the brain. The classical understanding is, of course, the billiard ball universe of Newton. And there's always been a problem. How do these bouncing billiard balls ever account for consciousness? They just seem to be totally different concepts. There's no there's nothing in the concepts of bounding billiard balls that would suggest that something like consciousness, which seems so totally different concepts, how one could come out of the other. And so philosophers have been wrestling with this problem since Newton, and somehow modern philosophers say, well, somehow the bouncing billiard balls are consciousness. That's the motion of the particles that is consciousness. And, they say that, but it's really difficult to grasp how that could be because the concepts are just not connected. So I think that accounts for Nichols' caveat, whatever that is, whatever consciousness is. Other people might say, well, the motions of the billiard balls produce consciousness. It's kind of the action kind of causes this other thing, which is definitely different in the opinion of many philosophers and seems very different. So the problem is then that all this is based on classical mechanics. Now, we all know that basically in the beginning of the 20th century, experiments began to be done which proved that the basic concepts of classical mechanics were false. And it was replaced by another theory called quantum mechanics. And what should be emphasized, and many people really don't appreciate, is that the most radical of the changes introduced by going from classical mechanics to quantum mechanics was precisely a change in the understanding of the connection between the mind and the brain. Quantum mechanics was devised to be a theory about relationships between conscious experiences. On the other hand, all the mathematical structure that was the basis of the theory was formulated in terms of mathematical structure of physically described processes. When I use the word physically described, I mean the following. A physical description is a description that assigns mathematical properties to space-time points. And that covers both quantum mechanics and classical mechanics. That's what we can mean by physical description. And, the problem with this, now, most people dealing with this problem want to believe, and with some justification, want to believe that everything that's big can be described in classical terms, but everything that's small, atomic sized, has to be described quantum mechanically. And that's kind of part of the lore. On the other hand, in fact, as Einstein emphasized, essentially big things are made out of small things. And if you know the laws of motion of the small things, that should lead to an understanding of what happens at the macroscopic level. And, what happens at the microscopic level is described by something called the Schrödinger equation. The Schrödinger equation is the quantum mechanical analog of the deterministic laws of classical physics. When you go from classical physics to quantum physics, the laws which were formulated one way turn into the Schrödinger equation. Now, if you agree with the idea, in fact, if you want to describe what's going on in the brain, at the chemical level, really you're needing quantum mechanics. So in some sense, in some fundamental level, and also tables and chairs. If you want to understand the rigidity of this table or the electrical conductance of some process here, you have to use quantum mechanics to understand it. So you're accepting the idea that big things are made out of little things. And now the problem is this. If you accept that idea that big things are made out of atomic size things, then you should be able to apply the laws of little things to predict the behavior of big things. But what happens is that instead of getting big things that are of the nature that agrees with experience, you get a smear of possibilities. That's another way of saying that the quantum mechanical evolution of the state of the universe or of any subsystem generates not the actual thing that is experienced, but a smear of possibilities for what could be experienced. And therefore the problem comes, well then, how do you make the connection between this smear of things and what is actually experienced? That's the problem of quantum mechanics. And so that's why at the core of quantum mechanics is the answer that quantum mechanics gives to that question. How do you relate what's happening at the physical level, which is this smear, to what you experience, which is some particular not smeared experience? Einstein gives the following example. And I should emphasize this because this is the basis of the whole problem and why we have to go to quantum mechanics and why it involves the mind-brain connection. Suppose you have a radioactive nucleus and you surround it by a detector and wire up the detector to a moving pen that writes on a moving scroll. It's kind of recurs earthquakes and stuff like that. So this pen, what you actually see is at some time, depending on the lifetime of the particle, you see a little blip, and then the reading below it says what time that blip occurred. And so your experience is you see a single blip someplace. But if you just follow the Schrödinger equation, this whole system, you find out, no, you don't see a single blip. You have a whole smear of possible blips if you just follow the Schrödinger equation. And if you follow that up one step further into the brain, which is presumably also made of atoms and molecules, then you find that the brain is a smear of possible experiences. And so that would seem to say if it just bubbles up, or if they're the same thing, then the conscious experience would have to be some sort of blurry thing over all these possibilities, but that's not what happens. So, how to deal with this problem? And the point is, in quantum mechanics, they give you an answer to this question: how to relate this smear on the one hand, which is what you get from thinking that everything is made of tiny atoms and molecules, into what actually is experienced by a human observer. And so that, just the fact that this is the problem is emphasizing the point that I made at the beginning. In quantum mechanics, there is the problem of the relationship between the physical, say the brain, and the mind is the central question, and you have to do a complete revision of classical ideas to address that question. So for a neuroscientist or somebody who's dealing with trying to understand the mind-brain connection, to use classical mechanics just does not make sense. We know that classical mechanics is wrong, and if you want to deal with the mind-brain connection, you've got to use quantum mechanics. And so, how does quantum mechanics resolve this problem? In quantum mechanics, you've got a lowest level description, which is the physical description. This is at the atomic level, and the Schrödinger equation is supposed to govern how that physically described part evolves in the course of time. How do we bring consciousness in? Well, the key step in quantum mechanics is to say that in addition to this underlying process that's going on here, described by the Schrödinger equation, you have to introduce something else. And that's called acts of observation. You have to bring observations into the underlying ontology as an extra thing on top of the physical description generated by the Schrödinger equation. So, these acts of observation and how they play into the system are described in quite precise terms. So it's not just hand-waving, and these are the terms that are actually used in order to make calculations that are in agreement with the experiments that classical mechanics cannot describe. So, the act of observation is a two-step process according to quantum mechanics. And the first step, and I'll give a more detailed description, but the first step is referred to as a posing of a question by the observer. So when we're talking about acts of observation are supposed to be associated with physical systems, subsystems, like the observer or like his brain or something like that. It's supposed to be associated with a physical system. And the act of observation says that it has to be two stages. And the first stage is a posing of the question, kind of putting a question to nature. And this question, like the questions in the game of 20 questions, are essentially yes-no questions. So the observer is supposed to pose a question. For example, if I'm going to do an experiment, in some sense, I've got to, I'm looking at some aspect of nature. So I set up this experiment or that experiment, or even if I'm thinking about something and thinking about wanting to do something even, it really involves making some choice between a lot of things that were formerly available to you. And the first part of this is choosing which question to ask. And this question in quantum mechanics is ascribed to the observer. The observer is supposed to make this choice. So this system, in addition to this physical part, is supposed to have something that we can associate with a choice of a yes-no question that the observer is, in effect, putting to nature. And then the second phase of this understanding of the mind-brain connection says that nature answers yes or no according to some specific rules that come out of the quantum mechanical formalism that's lying at the base of this thing. So you have this is your understanding of the mind-brain connection. You have, in addition to this thing that's occurring at the physical level, these acts of observation which have two phases. And so the first message is, well, if classical mechanics doesn't work, and this is the theory that quantum theory uses, if classical mechanics does not work, if you're examining the mind-brain connection, you ought to use quantum mechanics because use the theory that works in practice and not this other theory. Now, of course, most neuroscientists are not very familiar with quantum mechanics, and so basically this essential philosophical, metaphysical point is glossed over, and people say, well, big things should be described classically and little things described quantum mechanically. So what we're interested in consciousness is these big oscillations of the brain. That's somehow associated with a conscious experience. So that should be able to describe classically, and we can forget quantum mechanics. To be sure, if we want to go into the details of the chemistry, then we'll use quantum mechanics. But you make this split, which is not a logical split, and doesn't make sense ontologically or realistically, but that's what's done basically. And so you're throwing the baby out with the dishwasher or the dishwater if you make that move and say you're just going to use classical mechanics. You've got to use quantum mechanics. That's the first message of this talk. And so the next phase is talking about something that's very current. This is what I've been working on recently, actually, and which I was not going to be talking about. But it's nice to talk about something that's very current and exciting. This particular development is an experiment performed by a psychologist at Cornell, and it was it created such a furor that it even reached the pages of the New York Times, and where there were arguments back and forth about this paper. This paper alleged, or claimed to provide evidence, that the future can act on the present. Retrocausation is the word that's used. The future is acting on the present. And so this created quite a lot of outrage that this prestigious journal, psychology journal, Journal of Personality and Social Psychology, was going to publish this outrageous paper. And a lot of the people who wrote in were outraged that they should do such a thing. Others said, well, in fact, the editor said, well, I sent this to 4 of our top reviewers. They all found the paper up to standards, and therefore it's proper for science to publish this paper. And so eventually it was published. And but for example, Douglas Hofstadter was one of the contributors to this debate in the New York Times, and he said, you know, if any of what the psychologist that I'm referring to, his name is Darrell Bem, who I am told by people is a very much respected psychologist at Cornell University, and if any of what Bem says is correct, then it would topple all of the precepts of science that we know, or words roughly to that effect. And so that was the situation. This is a very hot topic, and there's a lot of debate, and whether the experiment will certainly be tried again in other universities. It's such a key point. And so we don't yet know whether other experiments will reproduce it or not. And of course, that remains to be seen, and we don't know. But I at least said, well, if it were true, is there some way of modifying quantum mechanics to accommodate it? And Hofstadter said, you know, completely topple everything we know about physics. Well, it turns out, not if you're dealing with quantum physics. In fact, it only takes a very tiny change in quantum mechanics to accomplish that, to be able to explain that data. And and in particular, this tiny change is, in some sense, a rational change, a more rational change. I had written in earlier books, and the idea that I bought into what Leibniz called the principle of sufficient reason. The principle of sufficient reason says that nothing happens without some cause. That there must be something that makes it be this and not something else. And Leibniz said it, but it goes way back to the Greeks. I mean, it's a part of philosophy, this idea of many philosophers that, you know, nothing should happen with no reason at all. And yet, in quantum mechanics, you have this random choice. Random choice just gives you the probabilities. It will be this or that. It doesn't tell you what actually is going to happen. So this is, from my perspective, and I had already essentially adopted that position a long time ago, that that's one place where quantum mechanics needs to be improved, and that although it makes perfectly good sense if your theory is only supposed to be a theory relating predictions of experiences, and there's a tremendous amount that you don't know, then the idea that there should be a random choice of this sort makes perfectly good sense, because you're saying there's all the stuff that you don't know, and if what you don't know is what's causing it to be what it is, then you aren't expecting to, in fact, in quantum mechanics, it says that you have to, in fact, average over all the things that you don't know. In fact, pretty much in classical mechanics too. You make an average over the things that you don't know about in order to make a statistical prediction. And so the following turns out to be true. This was, just from the principle of rationality or logic, I was inclined already to believe that there should be some reason for the choice. But that because you don't know what the reason is, it turns out to be statistical in practice. But at the fundamental level, there should be a reason. And, in order to, maybe I should explain, for your amusement, this BEM experiment. And it's something probably you'll all be hearing about. And this is a psychology department experiment, and the subjects are, of course, graduate students and various people, and they are told beforehand, before they sign up, you'll be shown some pictures, and some of these pictures may be erotic. So if you object to seeing erotic pictures, then you should not sign up for this course. When I said that to somebody earlier on, he said, yeah, and there's probably a line a block long to get into this. So in any case, there were plenty of people that volunteered to. And so what happens in the experiment, actually the experiment is 9 experiments, and the 9th one was not expected to give a result, and the other 8 all gave a positive result, and I'll just say what that means. So the first of these 8 experiments is the following. The subject is sitting before a screen, 2 screens, and he's told that there is a picture behind one of the screens, just a picture, and he's supposed to pick the screen behind which the picture appears. And so what really is happening is that after he's made his choice, there are 2 random number generators. One is, or pseudo-random, one is pseudo-random, one is random actually. One is choosing which of the 2 screens the picture is going to appear behind, and the other one is choosing whether the picture is going to be erotic or not erotic. So the chances are basically 50-50. I mean, if it's all chance, then it should be a 50-50 chance, no matter which, independently of whether the subject is erotic or not erotic. But what happens is that more than 53% for the erotic pictures, more than 53% choose the right screen, the screen behind which the erotic picture appears. But for the non-erotic pictures, the neutral pictures, it's 50-50. And this is, in one experiment, a 1%, probability of 1% it could be chance, and here you have 8 of them. So, and everybody, the experts who look at these seem to agree that the experiment is well done, properly done, and so how do you explain the fact that you get this deviation from the statistical probabilities? Well, there's an easy way to do that. In fact, what I'm going to describe to you in a few words actually is a long paper with lots of equations and everything to really make it absolutely a part of quantum mechanics, no question. And but the bottom line is this, something that's easily understandable just intuitively. If you say that nature's choice is not random, suppose nature's choice depends on something. Suppose it, in fact, depends upon these questions that are being posed by various observers. And suppose, for some reason, nature favors a little bit the choice of something that is going to be pleasing to the guys who are asking the questions instead of, in fact, there are 2 kinds of, there's a variation of this where the picture is horrible and you don't want to see it, and the same sort of result applies. So this, just suppose that there is a reason. Now add to it The idea is that, well, this reason is just not totally biased, and there's some little biasing in favor of pleasing the observers. Now, the justification for this is only, well, it explains, it's a simple theory that has some justification, rationality, and it does account for the data. And so that's what scientists do. They make a theory that will accommodate. And this is not a grotesque violation of something that is imposing something totally unreasonable on the physics. It's just a little variation of the current orthodox theory. So that if you do that, then two things. First, it explains the bias that these people are experiencing. Secondly, another part of this paper, if you, however, do the averaging associated with the fact that if you don't know or have no idea what the cause is, then of course you have to, in the formalism, you have to average over the possibilities. If you do that, then you automatically get the classical, the quantum mechanical rule that is given by quantum mechanics. So you do both things. You both account for the variation in these experiments, and yet the fact that normally, if you don't know what the cause is, you have to use the quantum mechanical rule. So let's see how we're doing here. So how do we account for example, this psychedelic, these experiments that were discussed by Nichols? And I should say, an important thing I did not add is what happens. We're going back to this act of observation. We're going back to the fact that it has the two parts, the posing of the question by the experimenter or the observer, and then the answering by nature. And the question is, what happens when nature makes this choice? And what happens is the following. When nature makes its choice, and this is what you do in quantum mechanics in order to explain the data that quantum theory has to explain. When the nature makes the choice, what happens is there's a collapse of the wave function. First, two things happen. First, the experimenter experiences the answer. The pointer is here. If I'm asking, is the pointer here or here? The first thing that happens is that the experience happens. Or not first, two things maybe happen together, but one is that the experience occurs on the one hand, and then there's a collapse of the wave function to the part of the wave function, say the brain, that is compatible with the experience. You've all heard of this collapse of the wave function. Well, eventually, in quantum mechanics, it amounts to something happening in the mind-brain connection. Whenever one of these experiences happens, corresponding to the choice on the part of nature to do something, to choose this, the corresponding experience happens, and the wave function correspondingly collapses to the part of its former self that was represented by, that's compatible with experience. And therefore, quantum mechanics, you're always kept up to date. The wave function is always compatible with the experiences that you are having. And so this is then, according to quantum mechanics, how you have to understand the mind-brain connection. There is this extra process. The first point is you can't just equate it as kind of what's happening at the physical level, because what's happening at the physical level is a smear. You can't do that. You've got to bring in acts of observation as something extra. So you have another process here. In addition to the process of the Schrödinger equation, you have another process that involves a choice, these choices that I'm talking about, and then the third process is the action of nature. So it's a more complicated structure, but at least that's the structure that works in quantum mechanics, and that's what quantum theorists essentially do to resolve this question. Now, where do I go from here? Okay, well, so talking about Nichols' experiment, let me. I'm going to get back to Nichols, what Nichols was telling you about what's going on in the brain. Let me bring in another interesting current thing. Stephen Hawking has written a new book called The Grand Design, and this book was written with a co-author, Leonard Mlodinow, who's a good writer. And so this book is very readable. I'm not recommending a book to you, but in any case, it's very readable, unlike some of Hawking's books, which are not so readable. So in any case, it's a very readable book, and I want to pull out of the whole book one sentence and then explain. First, I'm going to give you the sentence, then try to explain what it means and why it's important. The sentence is this, that in quantum mechanics, the observation creates the history rather than the history creating the observation. Now, the second part you kind of understand. That's the normal idea, that the history, whatever going on, then produces the observation. So what comes out of what has happened before, and out pops the observation. And so what does it mean when he says, in quantum mechanics, the observation creates the history? That seems kind of crazy. And yet that is really what happens in quantum mechanics in the following sense. If you... This next thing I'm going to say can be described either in ordinary Schrödinger equation language, the language that they prefer, that Hawking and Mlodinow prefer, is the language of Feynman sum over all histories. I don't know if you've ever heard this, but basically it's the idea that in order to make calculations about probabilities of a future event, you start with what you know here at the future, and then you look at all possible things that could happen, and you kind of assign numbers to them in such a way that then you can calculate, given any particular final state, what the probability is that that state should happen. So that's histories. See, the histories are what get you from the earlier situation to the situation now when something's going to happen. And the way quantum mechanics works is the following. It says that, well, we have the sum of all histories, and then this experience happens. Now, if you look at the details, some of the histories contribute a lot to this particular event, and some essentially don't contribute. They're contributing to other events, possible events elsewhere. So what you have to do in quantum mechanics is, if you want to make a prediction of the next thing that you want to predict, you've got to do the following operation. You've got to take this history that was covering all these possibilities, and then if this happens, then you cast out, you eradicate all of the histories that didn't lead to the thing that actually happened. And you need to use that in order to make a prediction of the next thing that you want to predict. Now, so, what's that all about, and what difference does it make? Well, the point is this. Suppose you had, here's the brain evolving, and suppose you had some measuring device that goes in and measures some process that's going on in the brain now, and then you want to make a record of it, so you move it far away, and here you have it over here. And before this event happens, if you were going to calculate what happens here, you'd have to include all of the histories that lead up to this event. But if you say, no, this event happened first, then you say, no, I'm only going to need to use I have to use, in order to make a calculation, only a subset of these histories that are compatible with the experience that actually happened. So that's the point of saying that the observation determines the histories. Because once you make the observation, then you eradicate most of the histories that formerly would have been contributing in order to calculate the probability associated with some faraway record. So this is occurring here. This faraway record can be space-like separated. And you make a choice here. You get nature chooses something here. You make a choice, nature chooses it. And suddenly there's, if you now want to calculate this, then you have to use the fact that you've got to first eliminate all the histories that didn't lead up to the one that you experienced. So the fact, what this boils down to is doing this experience, having this experience, causes you to change the history, effective history, the one that you need to calculate the faraway event. So that's the meaning of this idea that the observation creates the histories rather than the history creating the observation. See, in a classical model, the model evolves and things happen and the history determines what's going to happen. But that's not the way it happens according to quantum mechanics. So now, getting back to the talk earlier today about what's going on in the brain, you have to apply this idea then to these activities of the brain. And the point is, the brain is a very sensitive thing. There's all this energy available, and there's these little changes that you can make, and certain things become a stable system, but you just change small variables in a system that's highly energized, there's all energy available. Basically, it disturbs the possible equilibrium states, and so small changes in these parameters down here can change the whole dynamics and cause different states of equilibrium to emerge depending on. So there's no mystery, really, in the fact that small changes at these levels can make big changes in the dynamics because of all this energy that's available and it gets tapped, and it's a very complex interplay of all these forces. And so, of course, it doesn't take much of a change to make a big change in the experience. And but according to the quantum idea of what's happening, you have to realize that, well, all of these possibilities, before you make the observation, all of these possibilities are out there, and they're representing the quantum state of the system. And then this mystery of how consciousness suddenly emerges from this physical thing now has an answer. Well, there's another process. And this process forges a connection between a psychological dimension and the physiological dimension. Namely, an experience happens, and then all of the past history that did not lead up to this experience gets wiped out. So a big change is happening, and it's not just a mysterious bubbling up of consciousness from just another way of, this language that the consciousness is just nothing more than the activities of the brain, just doesn't make any sense at all in this framework. You understand this consciousness as something depending on something else that you add over and above the physical description, and this involves this two-part process, and also involves this collapse of the wave function to the part that's compatible with the experience. So you get, in that sense, quantum theory is giving you its answer to this question, and it's not just classical mechanics at all. And so that's the main message. And now, let's see. I like to ask questions. Let me turn over to question and answer if I can.
So what I'm wondering is, would there be an implication then that there was an initial point in time where essentially infinite possibility was there in the quantum state, and there was an initial act of observation that started the whole process?
Yeah, that's a good question. In fact, one of the questions that gets asked about this quantum understanding, in fact, let me give you a little background. I was working with Heisenberg, and I left and went back to Berkeley and wrote an article called The Copenhagen Interpretation. And so I sent it to Heisenberg, asking for his comments, and he said it was very good. He said not to change any wording, but just to pose a question that you should think about. What happened before there was any life in the universe? I mean, this is making everything depend on experiences happening. What happened before there was any life in the universe? And so this picture of the observation determining the history gives you a kind of an answer to that. I mean, let's suppose that we have a repetitious universe that keeps going on and forever. Somewhere in that chain, you might have a possibility for a conscious experience to happen. So if that first conscious experience happens, then according to this, all the rest of the history, in effect, gets annihilated. So as far as you're concerned, it's just as if there was only one history and it led to this miraculous occurrence of life or of consciousness. And so that's essentially a modern answer to that question. And so this idea that there's this collapse associated with experience and it changes the history, in effect, is my answer to that question.
All experiments in quantum mechanics turn out exactly the same way, whether there's a human being observing the experiment or whether it's merely a photographic plate observing the experiment. So my question is, how does consciousness enter at all when the observer, quote unquote, doesn't have to be a conscious living being?
Right. So this is also a very good, important question. Glad you asked it. One must distinguish, when talking about quantum mechanics, the Copenhagen interpretation from an interpretation that came very shortly after, which is essentially associated with von Neumann. And it was named by Eugene Wigner the orthodox interpretation. And it is orthodox in the sense that most mathematicians and philosophers who really want to understand this thing in ontological terms are almost forced to go to the orthodox interpretation of von Neumann, which is the one I've been describing to you. Now, the Copenhagen interpretation was the original one, and it's the one that's described in your courses in quantum mechanics. And the teachers in quantum mechanics and tell you, if you want to understand this thing, you divide the universe into parts below a certain cut, called the Heisenberg cut, or above the Heisenberg cut. Everything below the Heisenberg cut should be described in terms of quantum mechanics, elementary particles. But everything above the Heisenberg cut, you should use classical description. And so when you're talking about the device, that's within the Copenhagen interpretation, you're allowed to do that. You're allowed to say, well, everything above the cut, I'll put the detecting device above the cut, and then it can be described classically. And so this idea that big things can be described classically and little things have to be described quantum mechanically is part of the Copenhagen interpretation. But the Copenhagen interpretation is specifically designed to be a pragmatic interpretation, not an ontological one. There, in your courses and your books, it says, this question of ontological question of what happened, like at the beginning of time, or any of these questions, are not the job of the scientist. The job, in effect, they're saying the job of the scientist is to be an engineer, a glorified engineer, but an engineer who's only interested in, what works. If you do this, what's going to happen? Can you make statistical predictions about what's going to happen? And forget the ontology. Just say all it is this pragmatic description, and that is the Copenhagen interpretation, and that's the one basically you're referring to. But the problem is that these big things, these devices, are themselves made up of little things, and so is the brain. And if you want to, as I said, if you want to calculate the rigidity of this particle, the electrical properties of this, you've got to use quantum mechanics. So in some sense, it's illogical from a metaphysical or ontological point of view to make this split. And in fact, part of the quantum mechanical lore, and this was developed in detail by von Neumann, you can draw the cut in different places, and the predictions are supposed to be the same. That's great for pragmatic interpretation. But von Neumann says, well, then move it all the way up. And if you wanted to do ontology, want to talk about metaphysics and ontology, then you've got to move it all the way up so the interaction is really between the observer and, like, the brain of the observer and the conscious experience associated with it. So the answer to the question is this crucial distinction between the Copenhagen interpretation, which is pragmatic and says don't worry about these metaphysical questions. And in fact, there's a famous quote by Feynman that epitomizes this. He says, I don't understand quantum mechanics, and I don't think anybody understands quantum mechanics. And if you can possibly help it, don't try. Because if you do, you'll go down the drain just like everybody else who's ever tried. So Einstein tried, Feynman tried, Gell-Mann tried, all these people tried, and nobody succeeded in understanding it insofar as you're adhering to the Copenhagen view, because it's just not designed to be an ontological interpretation. And so don't try to understand these things. But if you want to try to understand these things, you've got to go to the von Neumann interpretation, because big things are made out of little things, and therefore that's the logical way to proceed. So in that sense, from the ontological point of view, from the von Neumann point of view, all of these experiences are really associated with what's going on in your brain and not what's happening at a device. You're just supposed to follow the equations until you get up to conscious experiences. And since conscious experiences are all we really know about, that's the consistent position of the Copenhagen interpretation. Are you about to get up and tell me something?
Yeah. One more question.
So getting back to the Darrell Bem experiment,
yes.
So if I'm understanding correctly, what it seems to suggest is that there's something about, we're human beings, consciousness occurs within a human being, obviously, and we don't just make observations, we also have emotions. In other words, there's some kind of valence, positive or negative, to the act of the observation. And in this experiment, it's associated with the erotic nature of the image. And so what that suggests is that there's something about the act of observation, the quality of the observation itself, that has statistically measurable implications as to where along the wave function it collapses.
Exactly.
So that says something about that. I mean, so it's not the universe making the choice so much as the observer, in a way, being the agent that influences where the waveform collapses. Whether or not we're conscious of it is a separate question, but I mean, it's basically what you're saying is that humans, as conscious beings, create their own reality.
Partially. And, as I was saying, this is a two-step process. If you want to bring consciousness in, it's two steps, and the observer has a huge role to play in this. He's got to choose the question. And if you look at your own understanding of what happens when you make a choice, if I choose to do this experiment, I had a reason for doing this. I wanted to find out something, and so I had a reason, or it might be an emotional thing. Maybe I do this because something else. I'm emotionally charge. So it seems to a person that his choice, this thing that this process, the first process here that's associated with the choice, does seem to involve some psychological dimension here. That the psychological aspects are entering into and combining with the physical, because the brain has got to be involved with this way. So it seems like the physical, like the mental, is entering in. So the personality of the observer and his personality, let's say, enters into this first choice. But then on top of this, there is the choice on the part of nature. Now, it's important that if you just adhere to the orthodox rules that this is purely statistical, if you adhere to those rules, you can't explain the BEM retrocausation effect. The orthodox rules are such that if you keep the orthodox rules, then orthodox ideas of causation basically hold, and you would not be able to explain the BEM retrocausation effect. So in order to explain that phenomena, you need to go to the next, within this framework that I'm talking about, you need to say that what's being biased here is the choice on the part of nature as to whether the answer is yes or no. So, in a sense, you're right. You know, the observer is playing a big role in this, and it seems like his conscious experiences are doing it. But the important point here is that if you look at quantum theory as it exists, there is no explanation offered by quantum mechanics as to what the origin of this choice on the part of the observer is. The quantum mechanical evolution, just at this lower level here, something else is coming in, and so this else that's coming in, there's two possibilities. One is this thing that's coming in that you think is your conscious experience really can ultimately be described in terms of some process, and the other possibility is, no, there is really an element, another part of reality here that we've got to deal with. It's different, and it can have some effects. And part of the talk that I was going to give was actually explaining how that model, without modifying nature's choice, just with the choice on the part of the observer coming in, you can explain how, by asking the right questions, the right timing, you can cause your physical actions to be the actions that you mentally intend. In other words, I have an idea, I'm going to raise my arm. And so I have an idea of what I'm going to do. And then, according to quantum mechanics, if I ask the right questions about nature and about what I'm going to see, and I ask them in the right timing, very rapidly it turns out, then I can actually understand how my conscious thought gets translated into the physical action, and the physical action being the action that your conscious thought is intending. So that was what I was going to talk about, but I decided I would get into this BEM stuff instead.